Hey, what's up, everybody? Welcome to Stoichiometry slash Solutions Part 3, where today we're going to go over colligative properties. So you might be wondering what a colligative property is. Well, imagine you have a solvent, something like water. We know that the properties of that solvent are going to be different if you add some solute, right? The properties of that solution are going to change based on that solute. And similarly, in colligative properties, we discuss the properties of solutions that depend on the concentration of solute molecules. So if you have some solute versus a lot of solute, what type of things change? And you might see from the definition that what we don't care about is the identity of the solute. So it doesn't matter what type of solute you're adding to the solvent. What just matters is the concentration of those solute molecules. There are four colligative properties: freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. I'm only going to go over the first two because they're like the only ones that really come up on the test. The other two are also really important, and we might come back to them later. But if you want to know more about them, then just do a quick Google search, and I'm sure you'll find like a lot of information on them. Okay, so let's get into freezing point depression. So consider what's happening when you freeze an object, right? If you freeze a liquid, you have molecules that are moving around. They are far more spread apart, and you have to bring them closer. And that's what this diagram here shows. So on the left here, we have a liquid, and on the right here, we have a solid. And the biggest difference that you can see is the space between those particles. In a liquid, they're a lot more spread apart, while in a solid, they're much closer together. And let's see what happens when we introduce a solute into the liquid. Let me just get rid of that real quick. The liquid and the solid. You can see how the solute molecules are within that liquid, but when you go to freeze the solution, those solute molecules get in the way. And so the space between the molecules are still pretty high. And in order to make it really go to a solid form, you need them closer together. And therefore, the freezing point goes down. You need colder temperatures to bring those molecules closer together because of those solute molecules. And we can calculate by how much that freezing point is going to lower. We have a formula that goes delta Kf equals Kf times the molality times the Van Hoff factor, right? So this is one of those weird instances where molality comes up. But really, let's dissect this equation before we go on to a practice problem. So Kf here is a constant, and it changes for whatever solvent that you're using. So in water, it's 1.86, but if for other stuff, it's different. I would remember the Kf of water, but they usually give it anyways, but it's still pretty important to know because water is the solvent that you're using for a lot of freezing point depression and boiling point elevation stuff. We're going to get to Van Hoff factor a bit later on, but remember, molality is just going to be moles of solute versus kilogram of solvent. Okay, so let's do a little practice. A solution that contains 55 grams of ascorbic acid, which is vitamin C, and 250 grams of water freezes at negative 2.34 degrees Celsius. Calculate the molar mass in grams over mole of the solute. Okay, so the problem tells us that when we add 55 grams of ascorbic acid, the freezing point of water goes from 0 degrees Celsius to negative 2.34 degrees Celsius. And so if we look at our formula, which is delta Kf equals Kf times molality times the Van Hoff factor, which we're given for now. Since we know that the freezing point goes from 0 to negative 2.34, we know that Kf is going to be 2.34. And you might wonder, shouldn't Kf be a negative value since we go down in value? But remember, what delta Kf means is change in Kf. And since we know it's freezing point depression, the number is going to be positive, right? So we know 2.34, and Kf of water is 1.86 times the molality times I. And so what we really need to calculate here is the molality. Molality is moles of solute over a kilogram of solvent. And in this case, our moles of solute is going to be based on the moles of ascorbic acid. And we know that we could calculate that by dividing 55 divided by the molar mass of ascorbic acid, which we don't know because I don't know about you guys, but I don't know the chemical formula of ascorbic acid. And regardless, the question asks for the molar mass. So we are going to need to determine molar mass of ascorbic acid anyways. Okay, now that we determine how many moles there are, we need to figure out the kilogram of solvent. And the solvent here is the water. We have 250 grams of water. And 250 grams is just 0.25 kilograms. So we know that 2.34 equals 1.86 times 55 over the molar mass over 0.25, and then times I, which is going to be 1. So we just multiply by 1. And if we do a little bit of math here, divide 2.34 divided by 1.86, we get that 55 over molar mass over 0.25 is going to equal basically 1.258. And then if you do a bit more math, we can get that the molar mass is going to be 174.87. And I didn't show the math because, yeah, that's the answer is like a little hidden there, but it's 175. Basically what you do here, you just multiply 0.25 times 1.258, and then you take the molar mass to the other side, and then divide 55 divided by 1.258 times 0.25. Just a bit of algebra, and you just isolate M, and you get that the molar mass of ascorbic acid is 175 grams per mole. So the key takeaway here is really this equation right here. It tells you how the freezing point depression is connected to a constant of the solvent, the Van Hoff factor, and the molality of the solvent. Okay, so let's move on to boiling point elevation. What happens when you boil a liquid is that the molecules themselves have a lot of kinetic energy from the heat, and so they jump up from the surface and they become this water vapor on the top. And we'll get more into this later, but when that water vapor on top is equal to the atmospheric pressure, then you start boiling. And so when you don't have a solvent, like here, it's much easier for the water molecules or whatever solvent molecule to jump up from the surface. But when you do have more solvent molecules, it becomes harder and harder for those solvent molecules to jump up from the surface and become the vapor. And that's why we have boiling point elevation, right? When you have more solute, you need more and more heat, and the boiling point goes up for those substances. Similar to freezing point depression, we have a formula that describes this, where it's change in TB equals KB, which is the constant, and it's the same for water, times molality times the Van Hoff factor. Fundamentally, it's extremely similar to the equation that we saw before. And similarly, let's do a practice problem to try this out. What is the boiling point of a solution prepared by adding 29.3 grams methanol to 0.0590 kilograms of chloroform? The boiling point of pure chloroform is 61.2 degrees Celsius. The boiling point constant for chloroform is 3.85 degrees Celsius per mole. And we're given that the Van Hoff factor is 1. Okay, so let's just write out the equation. Alright, so we know that the solvent is going to be the chloroform. We're given the boiling point of chloroform, and we're also given its constant. So we know that all the other stuff, the molality, is going to be based on the methanol. So before we start calculating the molality of methanol, let's just put in the information that we do know. We don't know change in TB because we're trying to find that. We know that KB is going to be 3.85. We don't know molality, but we know that I is 1 because it's given right here. And I accidentally put I here. That should be a 1. Okay. So how do we go about finding molality? Molality is moles per kilogram, and so we need to find moles of methanol. We know that we have 29.3 grams of methanol, and if we divide by molar mass, we're going to get the moles. And the amount of kilograms of solvent that we have is this much, 0.0590 kilograms. All right, so we're almost done. We just have to find molar mass of the methanol. And we can just do that by adding up all the molar masses. So carbon has a 12 molar mass, and hydrogen has a 1 molar mass, and oxygen has a 16 molar mass, and that all comes about to 156. So our molality is going to equal 29.3 over 156 over 0.0590. And that comes out to about 3.18. And now we have all the information that we need to solve the problem. We don't know TB yet, but we know that the KB is 3.85, and the molality we just determined was 3.18 times 1. So our change in the boiling point is going to be 3.85 times 3.18. And that's going to be 12.243. And remember, what this number signifies is the change in. So we know that boiling point is going to elevate, meaning if the previous boiling point was 61.2, we would need to add 12.243 to get the true boiling point now. And so the boiling point is about 73.44 degrees Celsius. And the answer I put 73.4. So we did it correctly. Again, key takeaway is the equation right here. And it's very similar to the freezing point depression that we saw. But in this case, the boiling point elevates, meaning the boiling point gets higher. And while we saw the freezing point depressed, meaning it gets lower. Okay, so a certain part of the equation that I've been kind of skipping over is the Van Hoff factor. And the Van Hoff factor is the ratio between the number of particles present after dissociation to the number of particles initially dissolved in the solution. What does that mean? Well, let's look at NaCl. If you were to put NaCl in water, which is NaCl is salt, if you put that in water and you made a solution of salt water, what you would see is that the salt splits up into sodium ions and chloride ions. So at the end, you have two particles, right? Na and then Cl. But when you put the NaCl first in, it's just one molecule. It's just NaCl bonded together on its own. So if you have a 2-to-1 ratio, that means your Van Hoff factor is 2. And that's what we see here. And so what NaCl was in this situation, it was an electrolyte. And an electrolyte is a substance that dissolves into cations and anions, and as a result can conduct electricity in that solution. So NaCl on its own can't conduct electricity. But when you put NaCl in water and it dissolves into those ions, that substance can conduct electricity. And so now we can break up the categories into non-electrolytes and electrolytes. And we'll see that the electrolytes, there are kind of different types of electrolytes. But first, let's deal with non-electrolytes. So non-electrolytes are substances that don't dissolve into cations and anions. Therefore, their I value has to be 1. They don't dissociate. So they start off as they end with 1 and they start off as 1. And a 1-to-1 ratio is just an I equals 1. You can see the examples here like glucose and sucrose and ethanol, methanol, urea. These are going to be large organic compounds. These compounds are held together by strong covalent bonds and a lot of London dispersion forces. And that's what gives it that non-electrolyte property, because when you dissolve them in water, their bonds are so strong that you can't overcome them. So if you see like a big chemical formula for like a substance, or if it's like organic, then it's quite likely a non-electrolyte. Okay, now let's discuss electrolytes. And you can break down electrolytes into two categories. The first one are going to be weak electrolytes. So when you dissolve those substances in water, only a couple dissociate. You can see here over here, there's a bunch of them. There's 10 of those compounds, and then when you dissolve them, only one of those compounds dissociate. And that's characteristic of a weak electrolyte. In a weak electrolyte, 1 to 10% of the compounds are going to dissociate. On the other hand, you have strong electrolytes, and these electrolytes are ones that dissociate 100%. All of them are going to dissociate, and that dissociation has a value. We value it as an alpha. So the alpha value for weak electrolytes are going to be 0.01 to 0.1, and the alpha value for strong electrolytes are going to be 1, right? Because it's 100%. And so you can calculate the Van Hoff factor using this formula right here. I equals 1 plus alpha times n minus 1. Many times you won't have to use this formula itself, because they will either give you strong electrolytes or they will ask you to compare strong electrolytes and weak electrolytes. So if you are given something like a strong electrolyte but its molality is super low compared to a weak electrolyte where its molality is super high, chances are the strong electrolyte is going to have more freezing point depression or boiling point elevation, because that I value is going to be a lot bigger. Okay, let's take a look at categories of weak electrolytes. So weak electrolytes are going to be weak acids and weak bases. And I added a list of common weak acids and bases. And it's recommended that you memorize at least some of these because they come up a lot in chemistry. And so these weak acids and bases only dissociate a little. That's the whole gimmick per se of a weak electrolyte, that they only dissociate a small amount. On the other hand, if you look at strong electrolytes are going to be strong acids and strong bases, but also salts. And so you have lists of strong acids, strong bases, and some salts. And if you want to memorize them, go for it. So again, strong electrolytes are going to dissociate completely in water, and you'll see that with your salts and strong acids and strong bases. And so you can usually tell their Van Hoff factor just by looking at their ions. So NaCl is going to be Na plus and then Cl minus. And so you don't have to go and do the whole equation to find the Van Hoff factor. You can just say, oh, okay, the Van Hoff factor is going to be 2. And if you look at something else like calcium chloride, CaCl2, well, it's going to break up into the ions, remember. So it's going to break up into calcium and 2 chlorides. So in this case, I is going to equal 3. I'm writing sideways, but I hope you can see that. Calcium chloride breaks up into 3, so you really need to know the ions here. And in strong electrolytes, your Van Hoff factor is just going to equal the number of ions that you have. I guess also this is where it comes in handy to know your common polyatomic ions, like HNO3, right? HNO3 is going to break up into H plus and NO3 minus. It's not going to break up into N plus and then O minus or whatever. It won't do that. You have a polyatomic ion, nitrate, and then you have hydrogen. So your Van Hoff factor is going to equal 2. All right, now that we've discussed the Van Hoff factor, let's do some practice problems based on these colligative properties. Which aqueous solution exhibits the largest freezing point depression? Okay, so we're given that it's an aqueous solution, so that means the Kf is going to equal 1.86. Aqueous just means that it's going to be in water. For all of these, it's going to be the same. So what we're really looking for is the number with the greatest molarity times the Van Hoff factor. Molality times the Van Hoff factor, sorry. So let's go through each one of these. KBr is a salt, so its Van Hoff factor is going to be the number of ions that it has. So it's going to break up into K plus and then Br minus. Van Hoff factor is 2, and so its molality times its Van Hoff factor is going to be 2.0. Okay. Let's look at the next one. We see C6H12O6, large organic molecule. Van Hoff factor is going to equal 1, right? And if we multiply that times its molality, we get 0.75. And so B can't be it because it's already smaller than our first option. Let's look at MgCl2. And it's going to be a strong electrolyte that's going to break up into Mg, chloride, and then chloride. And we know its molality is 0.5. So 0.5 times 3 is 1.5. Still not bigger than the 2.0 that we calculated for KBr, so C can't be it. Okay, let's look at the last one. Ga2SO43. Um, that's going to be a weak electrolyte. I believe it's a weak base. And so its I value is going to be low. It's going to have a low I value, and we see that its molality is also extremely low. So low times low, that means that is not going to be the largest freezing point depression. It's probably going to be one of the lowest. And that leaves us with KBr, which has a freezing point depression of 2, and that is going to be our largest freezing point depression. And we are correct. Okay, let's move on to the next one. Which aqueous solution has the highest boiling point? All right, so aqueous, again, we know it's in water, and that's going to have a 1.86 value. So again, what we're comparing here is going to be the molality times the I. Although we change from freezing point to boiling point, we're still comparing the same values here because remember the formulas are extremely similar. So let's go through all the 4 choices. All right, so let's look at CH3COOH, big molecule, organic molecule. It's going to be a non-electrolyte, meaning its I value is going to equal 1. So molality times I, it's going to have a 1 value. Let's look at H2SO4. H2SO4 is a strong acid, meaning its Van Hoff factor is going to equal to how many ions it has. So it's going to break up into H+, SO4, I value of 3 times its 1 molality. That means it's going to have a 3 value. H3PO4, weak acid. So its I value is going to be low times the fact that it has a 1 molality. It's not going to be one of the answers. And then the last one, C6H12O6, glucose, big molecule, organic molecule, I is going to equal 1, and it's also going to have a 1 value. And so these 3 are not it, and it has to be B. It has to be the second one. And we are correct. All right, let's do the next one. Which of the following is a weak electrolyte in aqueous solution? So weak electrolytes are your weak acids and your weak bases. So let's go through and see which ones are weak acids and weak bases. And so HF is actually a weak acid, so we can keep that. NaF is not one of those. NaF is a salt, and that's a strong electrolyte, so that can't be it. A hydrochloric acid, HCl, it's the face of strong acids, so that can't be it. And KCl is also a salt, and so that can't be it. And so HF has to be the right answer, and we are correct. An interesting thing about HF is that if you look at the column where fluorine is on, all of the H, and then some other value, so HF, HCl, HBr, HI, Cl, Br, and I, they're all strong acids, but the only weak acid there is HF. And it's one of those exceptions to the strong acid rules that I guess you need to have in mind. So it's good to know that HF is a weak acid, while its other brothers and sisters in the column are going to be strong acids. Okay, let's move on to the last question. An aqueous solution of potassium sulfate has a freezing point of negative 2.24 degrees Celsius. What is its molality? All right, so let's write out the equation. Okay, since we know that the freezing point is negative 2.24, that means our change in Kf is gonna equal 2.24. We know our Kf is 1.86. We don't know molality and we don't know I yet. let's try to figure out what the value of I is going to be. K2SO4 is a salt. And that means that it's a strong electrolyte, meaning it's just going to dissociate into its ions. So K plus, and SO4 minus. And that means its I value is going to equal 3. Alright, so we can plug that into our equation. Times M times, we know our I value is 3. And so if we just do a little division here, 2.24 divided by 1.86 times 3, we get our molality is going to equal about 0.401. And that is our answer. So we just used the equation to connect together all these different ideas to find the molality of this solution. So I hope you were able to follow along and you saw how we use the equation and how the freezing point and boiling point, elevation and depression, how they work on a molecular level. That's all I have for this lesson. I hope you learned something and I'll see you later for part 4.